non-convex, how come we are able to solve it with guarantees, right? And that's where we did the variational characterization. We asked what are the saddle points, what are stable points, or what are the second order local optima. And we saw under eigengap, there's only one unique stable point, right? And that was the maximum eigenvector, the first eigenvector. And so that's what gave this the efficiency that, or the ability to just do a local search method like gradient ascent and being able to recover the top eigenvector. Right, and I said similar characterization also holds for all the other eigenvectors. You can think in terms of Rayleigh quotient formulation, and so hence on top of it you can build these linear algebra methods that have guaranteed convergence, and that underlies the foundation, right, for all the other methods. And we saw some applications. The most basic was PCA, like how do we extract the principal components of the covariance matrix of your data, and the interpretation that you're then projecting your data points to a rank K subspace, right? What is the best fixed rank subspace to project your data that's given by the top eigenvectors of the covariance matrix. So we saw that correspondence between the spectral decomposition and the notion that we are projecting it to a low dimensional subspace, and hence the hope is, if you have high dimensional data, right, you can filter out the noise and only look at the main principal directions. And this is a standard component in many of the data preprocessing. And I showed you some other examples. We looked at the Gaussian mixture, and we said that this is a generative process for when you want to think about clustering, right? Like, we have clusters of your samples, and then now we said how spectral clustering, you can think of it as first doing PCA, so projecting to the components along the means and then doing clustering on top of it, right? And so we said this is a way to use dimensionality reduction to help us cluster better. And we said we'll do hidden Markov models today because we ran out of time, and that's where we had stopped, right? So that was the summary from last lecture. The main message was spectral decomposition of matrices can be very helpful in finding low dimensional structures where the main signal of the data is, or the main aspect of what you want to estimate is present, right? So that's where we stopped, and today, I'm going to extend it to tensor methods, right? And so the very first question will be why tensors? Like matrices seem awesome. We have so many methods underlying spectral decomposition of matrices. Why go beyond? And so for that, let's recap the Gaussian mixture model, right? So this is what we had from last lecture, and now we can see why tensors can be helpful, right? So if you recall, what we said was, so I'm going to rewrite it again here just to kind of give you the intuition of what, how we formulate this mixture model. So we have the mean vectors, right? So I'm going to put them as columns of this matrix A. So this is the unknown. So we want to estimate the vector of the means, and we assume the variance is just spherical Gaussian for simplicity. So this was the simpler case. So you just have the same variance along each direction, and that variance is sigma square, right? So that's our generative process, and if you and the main, I guess one aspect I wanted you to be comfortable formulating was to think about the discrete or the categorical variables in terms of basis vectors, right? So in this representation now I'm writing my Gaussian mixture in terms of h, which is a hidden variable, right? So h here is latent or hidden because you don't observe it. Like I'm not telling you from which component the data is drawn, right? So I'm hiding that from you. And I'm gonna say the values it can take are these basis vectors. So if I want to choose component k, the value h will take will be the kth basis vector, right? The standard basis vector. And I guess from last week you remember that is just 1 at kth entry and 0 everywhere else. And so is this formulation clear? We said that we can now express the Gaussian mixture, right? So X is the sample drawn from the Gaussian mixture as first selecting which mean component, right? So by having the basis vector, I'm selecting which column here, right? I'm selecting a column. And then I'm gonna, the Z is the standard, or rather spherical Gaussian, right? So I'm gonna just separate the two parts. So is this clear? So, and we talked a bit in detail last lecture that this is a convenient representation because I can precisely characterize what is the dependence between hidden and observed variable, right? And in this case, it's a linear dependence, and that'll really help us manipulate them better. And this is the underlying philosophy on a number of other models, right? So we'll go into hidden Markov models, topic models, and it's precisely the same notation, right? It'll be the same form, except the Z or this noise variable could be different. There's very similar linear dependence between the hidden and observed variable, but the actual process will have differences from one model to the other. And that's what also means the common methods that we can exploit to estimate various models. Right, so in last lecture, what we asked was, how can I manipulate the moments to look at estimating the Gaussian mixtures, right? So this is called the method of moments. And the principle is I'm going to estimate empirical moments from my data and then use that to estimate the parameters of my unknown model. And we said the simplest one is Gaussian approximation, right? So if you look at the empirical mean of your data and the empirical covariance, right, so you can do a Gaussian approximation. But then if I now need to express more non-Gaussian models, you would need higher order moments, right? So in general, the first and the second moment will not be enough. And that's the primary motivation to think about tensors, right? So if I only have only second order moments, that can be expressed as a matrix, but for higher order moments, we need to think about tensors. And so this is the method of moments. You could ask how does it relate to the classical maximum likelihood estimator, right? So if you've done statistics course, you would know, or in general you would know what's maximum likelihood estimate, because there we are asking, give me a set of parameters that'll maximize my likelihood, right? So I have the probability, let's say I observe x1 through xn, these are my samples, I can evaluate the likelihood of these samples, right? So let's say xi, have log of it, so it's easier to express in terms of log. So I can look at the, if they're IID samples, I can look at their probabilities or likelihoods and maximize. So I want to maximize the parameters, right? Rather, I want to maximize the likelihood and ask what is the model parameters that will do that. And so what's the challenge with doing this? So for a Gaussian mixture, what's the challenge for having a maximum likelihood estimator?
So they have a ton of free parameters and a lot of symmetry.
Is it
a lot of like free parameters and symmetry? And, like,
yeah, so that makes it non-convex, right? So you have these latent variables, and once you have a latent variable model, so if you recall the first lecture on non-convex optimization, we had brought up that example, right? So this is where maximum likelihood has no guarantees. You know, people do expectation maximization, which is a local search method for likelihood, right? So there's no guarantee it'll go to the optimal, globally optimal point, but it's a local method. So it's an approximation to MLE, but we have no guarantees of what that would be. And especially in high dimensions, if you have you know, like I said, the interest for us and in many practical applications will be where this ambient dimension D is very large, right? So you have like now these mixtures lying in maybe, you know, thousands or even millions dimensions, right? So you can have the data be living in a high dimensional space. And so there it gets, these problems can be having a lots of local optima, and it's not clear whether we can solve that efficiently. And in fact, in practice, we see, you know, it's not easy to have these methods succeed very well in high dimensions. And so that's now the question is, now can I come up with an alternative method for doing latent variable estimation, right? Like latent variable model estimation. And that's where there is method of moments, and it'll come with its own set of challenges, but we can ask, you know, what can I say in this setting? Right? And traditionally, people didn't use method of moments in statistics because statistical efficiency was considered to be the key. Right? So classical statistics was all about, I have very limited data, let me do the best thing I can. And usually my model parameters are in low dimensions, so I'm not looking at very high dimensional model estimation. So that's okay, computation is not the primary concern, statistical efficiency was the primary concern. But now we're in a different world, right? We typically have lots of data in high dimensions, but you know that can be ill-posed, right? So you hope for a low-dimensional manifold that can express that data. And so in this case, think of it as few Gauss mixture components, so the K is small and D is very large, right? And that's called the realm of high-dimensional statistics. And so we want to ask, you know, computation is a big part here, right? Like if I can't do brute force computation in high dimensions. So both computational efficiency is the key, and the statistical efficiency, at least in many applications, could take a backseat. And that's kind of the, you know, almost like kind of bringing back an argument for bringing back method of moments, although that didn't receive a lot of attention in classical statistics. So this is kind of a very quick background from statistics. So how many of you have like studied about statistical efficiency of maximum likelihood, or like the Lecam principle or method of moments? Any of these? No? Ring a bell? Okay. It's good to like do a quick stats 101 primer, right? Or more an advanced stats, like a I think a statistical inference course, I would highly recommend going through that, because that gives a different set of tools and different analysis than what we can possibly cover in this course, or even what the other courses in machine learning are covering. But anyway, that's kind of pretty much the only background I can give here in this lecture. So given this, let's now jump into method of moments, right? So now the question is, how do I use the moments to estimate the unknown parameters? So the unknown parameters here are A and this sigma square, right? So those are the only unknown parameters in this parametric setting. I'm going to say I want to fit my data to mixture of Gaussians, spherical mixture of Gaussians. So let's now see, let's kind of keep writing down the moments and asking, what we can say with them, right? So the first order moment, right? So if you recall the notation there, we said, between this change of categorical variables to standard basis functions, now I can right, the probability that, this variable h takes the basis vector I, which means it takes the ith category, is nothing but the same as, I can take expectation of h and then look at its ith entry, right? And we define that expectation of h, we'll call it as w. So this is the vector of probability of selecting each component, right? So it's really the proportion of data in each component. Is that clear? So all the probabilities now become expectations, right? So for discrete variables, all you need are joint probabilities, but now I can think of them in terms of just correlations. And that makes it very convenient.
Remind me, in this setting, are you assuming you know W?
No. So I will also need to now estimate W. That's what I realized I missed, so these are the three unknown parameters. Right? So we can start now writing down the moments and seeing, what information can I glean from that, right? So I think it should be intuitively clear that the first two moments is not enough, right? Because that'll only be for a single Gaussian, we'll need higher order. But let's see what the first and second moments give us, right? So let's say expectation of x, I'll call it mu, right? So how can I express this? What would this be? This is easy, right? Like, what is the mean of the Gaussian mixture? How can I express in terms of the components? I guess it's also there. Yeah, so, I'm just kind of making sure everybody is on board here, right? So it's nothing but choosing the component I with probability wi, right? And again, the benefit of this notation is I can, write all these expressions much more cleanly in terms of like matrices and vectors, right? That's the other reason, it's kind of much harder to see the overall structures with kind of summations and, it's the same thing, of course, but try as much possible to write them down in terms of matrix vector or matrix products. That also helps you interpret better. Right? And in fact, you can see that directly from this equation as well. If I take expectation of x, it's nothing but a times expectation of h. Right? So I'm just doing that a bit slowly because you're usually used to thinking of categorical variables in terms of interpreting the draws first and then looking at what the configuration is for each draw of the categorical variable. But you can directly interpret taking expectations here. Is that clear? Right, so that was the first moment, and obviously this is not enough, right? Like I'm having a times w, like this is certainly not enough. And so now, I can look at second moment, right? That's the correlation. I can also look at the covariance, which we did there. And the correlation is what? What's the correlation? I can just expand this, right? So what happens if I just expand this expression?
H and Z are independent, right?
Yeah, so H and Z here are independent, right? I guess you can, that is kind of, you can glean that because of the way the process is generated, right? I'm going to first select the component, right? And then all of them have the same variance. So and I'm going to use this notation as well to show independence. And conditional independence I will use, by the way, like conditioning. Yeah, so H and Z are independent, so the cross term will be 0 because the expectation of Z is 0, right? So the only terms that survive are this. So what would this term be? So what is expectation of Z transpose? Sigma square I, right? That's just it has 0 mean, so the correlation is the same as covariance. So what is this quantity? So what are possible values H can take? Yeah, so how do I interpret this? Right, so, let's write this down here. So, this is hopefully not too difficult, right? Let's expand it. So how do the only values it can take is EIs, right? So I can say EI transpose with probability WI. What is this? How can I write it in terms of matrix? And as I said, let's write it in terms of as much as possible matrix products.
Isn't it a diagonal matrix where each element
Yeah.
is diagonal from the W?
Exactly, right? So I'll use the notation diag of W. Right, so, and in the beginning, kind of doing it in terms of these basis vectors seems a bit strange, but you see, it'll be a lot more convenient eventually, so that's why I will. And if you recall from last lecture, we argued that, if you look at the covariance matrix instead, and look at the lowest eigenvalue, you can compute sigma square. Right, so as I said, the regime will assume is K is far, far less than D, right? So there are more ambient dimensions than the components. So that's the regime of interest to us. The methods will be very different if it's the opposite. So in this setting, if you recall this expression here, we said, the mean components can only add to the eigenvalues, right? And so the lowest one, this part will be 0, and you can look at the lowest eigenvalue and estimate the sigma square. Of course, there are sample issues. Here I'm assuming I can have the exact moments, right? I'm not yet come to that. We'll deal with it later. So sigma square is known. So here I can assume that I can cancel it out, right? Like if I know sigma square, I can just subtract that from the correlation matrix. So what I'm getting at is I have an estimation of this product, right? So I can estimate what the product of A with diagonal matrix, right? This unknown W and then A transpose. So if I knew only this product form, can I recover A? Can I uniquely recover A if I only knew this part? Or when can I uniquely recover A if I only know this product? Is it clear? Is the question clear? Right? From my moments, I can only estimate this product, right? And my goal is to recover both A and W. In what setting can I uniquely recover that? For what assumption on A and W? Yeah.
So there are eigenvalues and eigenvectors.
Yeah. So that means A should be orthogonal, right? So only in that case is it unique. and W is all non-zero, right? So there's no zero, so Wi, let's say. So in that case, I'm done, right? So if I had like these mean components be orthogonal to one another, and obviously I want non-zero eigenvalue. Actually, it's not just non-zero, you really want them to be not equal to one another, right? W1 not equal to W2. So if you recall, that's the eigengap condition, right? So if you don't have eigengap, you don't have a unique recovery, right? The eigenvectors are unique only if there is a strict eigengap. Otherwise, you will just have the subspace, and any selection of vectors from that subspace is equally valid. Right? So is this a reasonable assumption to make from the machine learning perspective? No, right? I mean, this is so weird. I mean, like, why can't the component have equal proportions, right? Like, saying that you can't do that is weird. And obviously, it's very unusual to expect that the mean components will be orthogonal to one another. And so what this is saying is only in a very special case can you just get away with having two moments to estimate the mixture of Gaussians, right? And so this is where we will need the third moment, but you can actually extract something out of this. So now if I have this second order moment with the sigma square cancelled, what can I learn about A? What information do I learn about A? So if I only have moments up to second order, what can I learn about this matrix A? Anyone? I mean, we just said we can do an eigendecomposition, right, of this matrix. So if you do the eigendecomposition, how is the eigenspace related to A? Yeah, so it's the span, right? It's even there, right? So I can recover the span of the matrix A, right? So by doing the eigendecomposition, I know that the span of A will be the nothing but the eigenspace, right? They're both in the same subspace, right? So that's where I can get up to, right? I can get the subspace in which the mean vectors lie, but I can't exactly estimate what they are. Right, and we are looking at the regime where K is much less than D, so we are looking at a low rank estimation, right? So the span is valuable because it's some low dimensional subspace compared to the ambient space. So it is still useful information.
Looking at singular vectors in this scenario, right?
I mean, eigen, right? It's symmetric, right? So these matrices are symmetric, so they're the same. Yeah? So that's what we can do up to the second order moment. Right, so is this clear? Because we'll now jump to tensors, and I really want the understanding of the second order moment, the eigen formulation, everything very clear here. That's why I'm going slow. Because once I jump to tensors, it's like a generalization of each one of these concepts. So once this is grounded, it'll be a lot clearer. Any questions here?
If you just use the first two moments, would that give you like a biased estimator?
So the bias is in terms of like in expectation, like when we talk in statistics, right? Am I getting the right estimate? And so if you're using the first two moments, I don't even currently have an estimator. Right, so I'm not, I don't even have an answer right now. I'm only getting some partial information about the parameters. Okay, so now let's ask, how do I recover the actual columns of A, right? Not just the span, but the actual columns. And this is where So if you look at the traditional literature, right, like before method of moments, one possibility is through clustering. Because what can I do with clustering? The spectral clustering we described last week was, first I'll project it onto this subspace, and then I'll do k-means or any other clustering method, right? But what is the downside? The downside is, this distance-based clustering will only succeed if I have good separation, right? If my cluster points are too close to one another, you can't really, have a good accuracy in clustering. And that's when you cannot use these methods, right? So that, that's pictorially, I guess you can see it very clearly. If I have large variances, if my sigma square is very large, right, all the components will just mix with each other a lot. So you can't do clustering. Right, and in fact, in high dimensions, this requirement of separation will be really stringent and not realistic. Like, for k-means and all these methods to succeed in high dimensions, even if you did spectral clustering, the theoretical guarantees hold only if you have very high separation, like square root d in d dimensions or something of that order, which can be too unrealistic in many settings. And so that's the reason to not go with clustering mechanisms, but to ask, with the method of moments, can I even estimate parameters even if I don't have separation, right? Because it's not looking at the ability to put the membership of the points through some distances. Okay, so this is just a short tangential direction to say when clustering works and when it doesn't. Any questions here? So given this, let's now go to the third order moment and ask what we can do with this. Right, so the main thing I want you to think about is this notation, right? So how do we go from a matrix to a tensor? And when we are using that to express the moments. So I just wrote down the second order moment or the correlation matrix, right? So for the correlation matrix, right, it's very, it's easy to see how each entry in the correlation matrix looks at the correlation between, let's say, the I1 and the I2 entry, right? So you can look at every entry here and say it corresponds to correlation between two coordinates of your random vector, right? So we're all, very familiar with the matrix. So we'll now extend that to tensor by saying, let me now look at the correlation of three coordinates, right? And that's expressed in the corresponding entry of my tensor. So is this notation clear?
Are tensors three-dimensional or are they n-dimensional?
In general, they can be n-dimensional, but the natural starting point is now 3. So everyone is on board with this notation, right? And in fact, that's the outer product notation, and that's what it's, that's a rank 1 tensor. So we'll come to that notation as well, and the notion of rank in a tensor in a bit later. But the main thing is now we're going to write down the third order moment, right? And the analogous thing is I'm just looking at every triplet of coordinates and looking at their correlations. Okay, so now let's write down the third order moments. So for the Gaussian mixture, how can I write down the third order moment? So as we said, if I know sigma square, I can cancel out components that correspond to sigma square, right? So in the beginning, let me even just do just the mean part, right? So let's mostly worry about this. We can do the full thing in a bit. So how can I look at now the third order moment? So before I even do that, let's just do the third order moment of H. So how do you think I can do this? So we did this for the matrix, right? So it's there on the board.
It's going to have a similar structure to identity, but in this dimension, so diagonal components are all the same, it should be 1.
Exactly, right? So if I expand it, it's like with probability Wi, it'll take EI, sorry. And this is actually like a diagonal tensor now, right? So we were writing diagonal matrices. Now think of it as a diagonal tensor. So it's like this diagonal here, right? So it's like this diagonal going there. And it's only non-zero along those diagonals. Yeah? And so now, okay, guys, so I know what this is, right? So all the randomness here is only in terms of H, right? So how can I expand this moment? So hint again, what would, how can you interpret this for the matrix, right? Let's first just write it for the matrix. So we said this is the same as the transpose, right? So and so in this case, we had now A diagonal, A transpose. So how can I interpret this? Any thoughts? So what is going on here? I guess the other, the expansion will make it, I guess, clearer, right? So let me just try expand this. So let's say mu I was the I. So let me write it in this form. So at least in this formulation, right, in this form, can you think of what a similar expression will be for the third order?
Should get like a weighted combination of the I columns of A weighted by the probability of.
Exactly, right? So this one I can rewrite it in terms of, this is the same as the outer product on these, doing it twice, right? So now with this notation, I can write it in terms of this, the same thing for the triplet. Yeah. So is everybody on board? And so this is where we'll now look into, this also has k components, right? This was so all we did was instead of taking out a product twice, we are taking out a product thrice. Okay? And so now the question is, if I have just this form, right? So I can compute, as I said, let's ignore the other terms, I can cancel it out. So I can tell you what the overall value of this is, right? So I can tell you this overall tensor. Now the question is, can I decompose and find the individual components, right? What the mu i's are. And so this is called tensor decomposition. So just as we asked the question with matrices, right? So with matrices I asked, given this expansion, can I uniquely determine what the mu i's are? So now I can ask the same question with order 3 tensors. Okay? And there are different forms of tensor decomposition. This particular form is called CP. It stands for canonical decomposition, parallel factors. So there are so many different names for the same concept. So they just kind of shorten that to CP. Right, canonical decomposition, parafac, they all mean the same thing. Yeah, so that's the main question, right? So what's so special about order 3 that we couldn't do it with just order 2, right? So we said with order 2, the conditions are way too stringent. If you recall, I needed these to be orthogonal, I needed this to not have the same value. And so now the question is under what conditions can I uniquely determine these components, right? And that's called identifiability. So forget about how hard it is to compute, right? That's the next question. Can I even have the hope of uniquely identifying the parameters from this, given this tensor? Okay, and so this is the first kind of, so what does your intuition say? Do you think the conditions for identifiability will be weaker or stronger going from order 2 to order 3? Just intuitions, I mean, need not. What do you think? No one?
It's more often unique. It's unique more often.
So, meaning the conditions will be weaker,
Yes,
right? And why do you think?
because we have more equations to satisfy. But
Exactly.
not that many, the number of equations to satisfy grows sort of faster than the number of parameters that we're playing.
Right, so here we are saying like now it's expansion of these k rank 1 components, right? So each one we'll call it rank 1, I'll come to that in a minute. And so we are now having these constraints, right, that'll involve more kind of variables or more, it's more stringent than the matrix case, right? And that's kind of the reason why you can expect uniqueness in the case of a tensor that you cannot for a matrix, right? So the thing is, not only does the tensor grow, the tensor is obviously bigger than the matrix, right? There is d times more entries here than in the matrix, right? So this is, let's say d squared, this is d cubed. But also the constraints, right? For something to be a rank k tensor is much more stringent than something to be a rank k matrix. So I'll just define, so for this identifiability first we need to say what is a rank k tensor, right? So for that, what is the rank 1 tensor? So what's a rank 1 matrix? That's a symmetric, I mean we'll do everything with symmetric because it's easier. So symmetric, we all saw that, right? I mean symmetric matrix rank 1 is just U transpose, right? But I can also interpret this in terms of the entries, right? So if I look at ijth entry of the UU transpose, that's nothing but UI times UJ. Right, so if it's rank 1, it's really this product of the corresponding coordinates, right? So that's how I think of the rank 1 matrix. Now we want to do the same for the tensor, right? And we saw this is nothing but the same as the outer product notation. And so same with the tensor, right? So if I now look at a rank 1 tensor, right? So I'll have to be able to express all the entries of the tensor in terms of just product of the entries of the corresponding vector, right? So that's all you need to express the overall tensor. So it has this complete decomposability, right? That's the intuition behind rank 1. And so on the rank k is the extension to that you can now express it in terms of sum of such k rank 1 tensors. Yeah, so it's the direct analog of the matrix decomposition now to tensors. Okay, so given this, so why? So now we can ask, when can I identify unique properties? What can I say about tensors, right? So between matrix and tensor, a lot of things differ. So first of all, with the tensor, this is not the only definition of rank. This is not the only possible decomposition. There are other forms that will be different, and so that's why there is this term CP, right? It's a special form of rank, and there are other definitions of rank. So we won't go into that here, but it's kind of like, so many things get much more complicated with tensors, and that goes with rank, right? So rank has many definitions, but also like how large can the rank be? Right, so for the matrix, what's the maximum value for the rank? In D by D matrix? D, right? But for a tensor, right, the CP rank can be even larger than dimension. In fact, it can be as large as D square in third order tensor, right? So, and that's kind of from parameter counting, you can see that, right? Because you have only like, so you can have a lot more kind of decompositions because you need to fit D cube such, the D cube tensor, right? The number of entries is D cube. And so you can have rank be large, and like computing all this is NP hard. We'll see in a minute why the problem gets harder to compute this, but not for a matrix, right? And now the question is, what are some easy cases, like what are cases where there are good polynomial time algorithms to compute this? So now what we'll do is we'll do a similar variational characterization that we did for matrix in the previous lecture. So we can ask the same question, like what is the the cubic form, which is the analog of, in the matrix it was the quadratic form. Right, so we wrote an optimization problem for computing the top eigenvector in a matrix. So we'll do the same with the tensor, and that's kind of the starting point, because if I can compute the top component, then I can hopefully compute the rest. Right, it's, so we'll start there, and I think that's very useful because you can see how the optimization landscape changes between the matrix and the tensor. Yeah, so let's say, so I'll need a notation for this. So let's say T is my third order tensor. I'll also keep it symmetric, so everything becomes easier with symmetric. It's actually called supersymmetric in the case of a tensor. That means it's symmetric in every possible way you transpose, right? So we'll assume that, and then I'll use a contraction notation. So we'll think of, let's say, contracting this tensor with a vector u. So if I contract this in, say, the first mode, right? So the mode here, so when I rate T of, say, like if I want to express the ij kth entry of T, right, then I can think of the different modes, right? So I is the first mode, j is the second mode, k is the third mode. So these are the three directions of my tensor. And so now what I'll describe is this contraction operation, which is essentially, think of it as contracting the tensor along one of the dimensions, right? So for the matrix vector product, I can do the same, right? So if I'm taking the matrix and multiplying with a vector, that's nothing but I'm selecting the columns of the matrix and multiplying with the corresponding entries of the vector. Right, so let's say M is like having columns M1 to M, let's say D. So this is nothing but I can write it in terms of the ith column of M with value Vi, right, the ith entry of V. And I'm just rewriting matrix vector product. Right? But this interpretation is useful because the idea is I'm selecting each column of the matrix and multiplying it with the entry of the vector and taking a linear combination. Right? So what I'm doing here is a linear combination of the columns. Right? That's what's a matrix vector product. Yeah, so everybody comfortable with that? So we can do the same with the tensor. Let's say now I want to just operate it in the first mode. So the other modes I'm not going to change anything. This is nothing but the same as a matrix vector product. But instead of here I'm like taking the columns, right? Here I would need to take the fibers. And so the way I will kind of think about this is, let's say I have ij kth entry. Right, so, but I only need to kind of think about the ith mode, right? So there is ui and I. So I'm only summing up over I, and the j and k are the free entries, so I'm just going to say like, by this notation I mean, I'm taking the full matrix on the ith slice. Right, just as I was taking a column here I can look at the third order tensor and slice each along each mode. So each one will be a matrix. Is this notation clear?
So you're summing up matrices there?
Yeah.
Okay.
So if you contract this third order tensor with a vector, that means you're reducing the order by 1, right? The result has to be a matrix.
In general, that holds with all dimensions, you're doing contraction.
Yeah. Right, so if you now instead contract here, that means that'll be the index over which you will run through and just do the combination. Right, so this is contraction, yeah.
Do you use Gaussian notation? Or acting convention?
This is the convention, yeah, so I'll use this notation. So more generally, right, so I can like take a tensor, I don't need to just contract it with a vector, I can also contract with matrices. In fact, I can contract with other tensors, but we won't get into the more complicated one. I mean, just as you can multiply matrix with another matrix, you can do the same here, right? So the general notation goes something like this, right? So I can use different matrices along different modes, and that's nothing but I'm taking like, right, ij kth entry, there is one index that is the ith one, and then I will have like I prime k prime, right? So I'm going to sum over, in this case I'm like multiplying over all the modes. Right, and this is now this new tensor. If I now, ask about its I prime, j prime, k prime entry, that will be this. I mean, if you recall your matrix product, right, you can do that special case, right? If you don't have this index k, right, if you don't have this, that's a very similar interpretation, right? Because in that case, it will be multiplying 3 matrices. So we are just extending that to more modes here. Okay, so that's a general version, but don't worry about it. It's just, the notation looks messier, but the main interpretation is along different directions, you're multiplying with different vectors or different matrices. Okay, so the notation seems heavy in the beginning, but intuitively, if you understand what's going on, that makes it very easy. Okay, so like, we won't need this right away, so let's not worry about this. And so instead, so we can now ask this question, right? So we wanted to maximize the cubic form. So we did the quadratic form for the matrix, so I'll write this side by side. So for the matrix, we said I want to maximize, let's say, U transpose MU, right? So over U, which was on the sphere. Now I can ask the same for a tensor, right? And this tensor contraction is the analog, right? I'm going to contract the tensor along each direction with U. So I will now have U, U, U. Right, so if I now, if I wanted to use this notation, right, so I'm also going to do the same over the other columns. So, you can write in terms of like, so there is UI, UJ, UK. This is also over JK. Right, so this is the notation. So I can do the Lagrangian as I did before, right? So the Lagrangian, you have the same definition. I'll just move the constraint to the objective and fix lambda. So here what did we do? We did this. We said minus lambda U transpose U minus identity. We will minus 1. We'll do the same here. So I'll add this 3 by 2 because I want to kind of, get the same analogy as the eigenvector, right? So I can obviously add any multiple here, and it's it's the same principle. So this is over U. And so now again, I can do the first order, second order conditions, everything as before. So if you recall, what did we say here? The first order condition was the eigenvalue condition, right? And of course, I want the constraint that it's on the sphere. So what do you think is the analogous condition for now the third order tensor? No, we just need to take a derivative with respect to U. What would that be? You have this form here, right? So if I take derivative with each one, the idea is that entry will kind of go away, right? So it'll be a vector, right? Then it's still, these two modes will be there, but it's symmetric over all of them. So it'll be like nothing but 3 times like T of U, and then this is identity, or like there's nothing, right? So in the sense, you're not operating on this mode, it was only these 2 modes. And they're all symmetric, so, so it doesn't matter which one you keep. And this is the same as, this was only still twice because it's the norm square. So it's still 3 lambda U. So I can just subtract the 2. And this is now the definition of an eigenvector of the tensor, right? So for the matrix, it was just like taking the matrix vector product and saying you will be stationary there, right? So if I multiply my matrix with this vector, I won't move. And I can do the same here, but I need to multiply it twice, right? So along 2 of the directions, I should multiply with the same vector, and then saying the output, I'm still not moving, right? The result is a vector, right? Because if I take a cube and multiply along 2 of the directions with vectors, right, I'm reducing those 2 dimensions. And then the result is a vector. So is this clear? So this is the definition of the eigenvector of a tensor. So what's the main difference you see between the matrix equation and the tensor equation? Which one is harder to solve? It's kind of hopefully obvious, right? Which one is harder to solve? If I ask you to solve this equation, huh? Why? Like, why is the matrix one easy? Linearity, right? So the linearity is the key. This is now linear in U, whereas this is quadratic in U, right? And this is quadratic in many dimensions. It's not a scalar quadratic equation, which is easy. The vector quadratic equations are hard. And that's where the hardness comes, right? So what's the maximum number of solutions you can have here for the matrix case? D, right? So you can have at most D eigenvectors. You cannot have more than D eigenvectors, right? And that's because for a linear system, you can't have more than D solutions. Whereas here, you could have an exponential number of solutions. So the number of possible, eigenvectors can be exponential in dimension, right? And that's rather that, it depends on other things, but it's certainly not just D, right? You can have a lot more eigenvectors. And so that's kind of the, and if you recall the second condition here, something nice happened, right? So if you recall, the second order condition was something like this, right? And we said like, for this to be a stable optimum point, we needed this to hold for all v less, perpendicular to u, right? So I'm just quickly writing the condition from the last week, and we said, oh, something magical happened, only the top eigenvector satisfies this. So we can certainly not hope that's the case there, right? So in general, you would not have this. So, but there is actually something nice if you take a special case where you assume that the columns are orthogonal. So let me, maybe even I'll use a different notation because let's say the tensor actually had this decomposition where all the UIs are orthogonal to the other UJs, right? So, this is true for every matrix, right? For a matrix, for a symmetric matrix, I can always find an orthogonal decomposition. For a tensor, that's not true for a general tensor. So it will have some CP decomposition, but that need not be the orthogonal. So the most compact decomposition need not be an orthogonal decomposition. And so this is a special form of tensors. So if we'll call them orthogonal tensors, and that's a special class, like it's not all the possible tensors. And so that's the, so for general tensors, yeah.
For orthogonality in higher dimensions, we can find the inner product to be the trace inner product on the tensors as you go up.
No, he will define it in terms of just the components.
Okay.
The components are orthogonal, because we are still writing the components in terms of just the vectors, right? Yeah, so, so I won't derive the full result, but this is something I'll ask you to verify. But it turns out for these orthogonal tensors, the second order conditions says that, there won't be one unique local optimum. There can be multiple local optima, but the only local optima are just the UIs. Right, so the underlying components will be the only stable points. So you could have lots of saddle points, right? So in fact, because this is a quadratic system of equations, this can be very large. But somehow luckily in this special case, if we look at orthogonal tensors, the only ones that are stable are the components. And so that's kind of it gets a lot harder than the matrix case, but there's a nice class within tensors where it's still easy enough. Right, and that underlies a lot of guarantees on how we can use tensor decompositions to still solve a large class of problems. So I didn't derive it here, but hopefully you will see the contrast why going from order 2 to order 3 makes things a lot harder, right? Because from linear, you lose linearity, and once you lose linearity, can get a lot more solutions, and it's, yeah.
Sure. If you have an orthogonal decomposition like that, could you not just apply the second order? If the UI are orthogonal, then can you just stick with the second order moment?
But we saw, if you recall, for estimating Gaussian mixtures, that wasn't enough information. Right? I could only tell you what the subspace of the vectors was, but not the true vectors.
But we could, if the UI and UJ are all orthogonal.
Yeah, so that's how we'll relate it to, this is still not directly useful for me because, I need to solve the non-orthogonal case, right? But there is a way to connect the two. I'll come to that in a second. Hopefully that's something I can cover. But yeah, that's the next part. We'll ask, how is this result, how can I use it to solve Gaussian mixture, right? But by itself is the result, at least you see like intuitions of how the problem gets harder, but you can think of a similar variational characterization. Okay? So now how can I use this methodology, right? So it turns out, before I go that, let me just quickly tell you, if it is an orthogonal tensor, how can I solve this? So maybe I'll keep this because I will, use this. So before I come back to Gaussian mixture, let's see how, if I had just an orthogonal tensor, how can I solve this? So I just told you the optimization landscape, right? So I said the optimization landscape is still nice, right? So the only stable points are just the components themselves. So that means I can do like a gradient ascent, right? Like I can do a power method similar to the matrix case. And if my goal is to recover all these components anyway, that's okay, right? So I won't just converge to the top eigenvector, I may converge to the other ones. But these are all parts of the decomposition. I want to recover all of them. And that's kind of the basic idea, that you can still, hope to recover, right? So the tensor power method is like taking now contraction along two of the directions, normalizing it, and just repeating this again and again. So just as you did for the matrix, right? Sorry. So if you recall, for the matrix we did the same, we'll do the same for the tensor. And one quick thing why these UIs are actually solutions, right? Because if it's orthogonal, right, if you are at one of the UIs, right, you will get back UI, right? So it's clear that they're fixed points. But because of the stability result, you're also guaranteed to only converge to them, right? So as long as you start from a random initial point, it's okay. You can have different randomizations. You can go to these stable points.
How do you define the orthogonal tensor?
This way. Yeah, so you're going to assume like there are some k components where each UI is orthogonal to other UJs. So same analogy as the eigen decomposition for the vector, matrix case, right? So the same extension.
To be clear, do you know the number that was given this tensor you're using as problem? Do you know the number of eigenvectors that exist?
Let's say we do. It's not, otherwise you have to kind of keep checking and looking at reconstruction error.
My two follow-up questions are, do we have the notion of multiplicity for eigenvectors in a sense? And then with this optimization, everything you said, you start randomly, you find these fixed points, but there's many of them. Right? Is there a way to, once you find one, to find the next one, to reduce the tensor you're working with?
So you can subtract out that component, and so that way now when you reinitialize, it's very unlikely. In fact, if there's no noise, you won't converge to the same, right? Because you've subtracted it out. So you can do, and that's the similar thing you would do in the matrix case, right? You would subtract one by one, so you can do the same here. So that's why like orthogonal tensors, right? In terms of the system of equations, they are much more complicated. They're a quadratic system, but they have some very nice properties that make them have similar properties as the matrix case, right? Whereas for the general class of tensors, that's not true. Okay, so let's say I can completely tell you what each of the UIs are. So if I'm given an orthogonal tensor, I know how to solve it. But then, the whole point for moving to the third order was that, no, I don't want orthogonality on my parameters, right? So let's come back to our Gaussian mixture case. And here, I don't want to impose that, that these should be orthogonal. So here we'll use, so something that we did last week, rather last lecture. So let's say these are my vectors. I can't do it in many dimensions, right? But picture that they're in d dimensions. They're not orthogonal to one another, right? So they can be in general position. So instead, I want to rotate the system, right? I want to do a linear transformation on the system, let's say with this matrix W, such that the resulting system will be orthogonal. So let's say W transpose A. Remember, A was my original matrix that had these mu i's, right? Should be rotation. So this, we'll call this R, which is a rotation matrix, meaning, this is set of orthogonal vectors. So sorry, R is a matrix, not a vector. So what is such a transformation? We did this transformation in the last class. If I have a set of vectors that are in some arbitrary position, but I want to multiply them, right? I want to do a linear transformation such that they become orthogonal.
Whitening.
Yeah, so this is the whitening transform, right? So what I really want is this W transpose A times its transpose, which is A transpose W, should be identity. Right? So if I can do this somehow implicitly on my data, then I can get an orthogonal tensor decomposition. Right? Because first I can do a linear transformation of my data, and then I'm going to do the third order moment, which will be an orthogonal tensor. So now the question is, how can I do a whitening transformation directly on my data? Like how do I get this whitening matrix? So if you recall your second order moment, what did you have? Right, so you had the product of this, if you recall. Right. So essentially the columns of A were reweighted with entries of W, but that's still okay, right? So instead of now these mu i's, I'm having it's just rescaled. And I can worry about getting the scale later, right? So even if I can recover each one of them here, right, then that's still okay. And so what we'll do is we'll use that to find the whitening transform. So meaning give me a W such that this is identity. Right, so if I did this whitening transform, I can essentially find a way to change my data, rather change the system, right, change the decomposition I want to recover into an orthogonal system. So I'm not doing the entire math, but I'm kind of hopefully giving you the intuitions that this is so I'm still using the second order moments to transform first my data into an orthogonal system, and then when I compute the third order moment in this orthogonal coordinates, right, rather on this transformed data, then I know how to recover the components. Right, so in a way, even though we can only solve orthogonal tensors, I have a mechanism to convert my data such that the moments we'll use will be orthogonal systems. Okay, so so maybe I'll give you some exercises in the assignment to kind of go through those derivations, but that's the overall intuition that you can use both the properties of the optimization landscape of orthogonal tensors as well as properties of linear transforms, right, like this whitening, to solve the problem. So now if you had like exact moments, you can exactly get the parameters. And so the main, I guess, question of when is identifiability, like what you need is invertibility here, right? So I can take my data, whiten it. So from my whitened data, can I go back? And for this, what you will need is A to be linearly independent. So if you recall your linear algebra, right? So if A is linearly independent, if you whiten it, right, so the dimension of that space will be K if the K columns are linearly independent, right? So that's when you have perfect invertibility. Okay, so and this is like much weaker, right? So in fact, this is just saying generic positions. So if I just take arbitrarily some vectors, K vectors in my d-dimensional space, they will turn out to be linearly independent, right? If I randomly sample, I can get linear independence. So these are called generic parameters because, it takes some special parameters not to satisfy this condition. Okay. So just by going to a third order moment, we came up with a very, almost a natural and a simple condition for recovery. Right, so the condition became a lot weaker compared to the matrix case. In matrix case, we said this should be orthogonal, but if I tell you moments up to third order, you can actually recover with just linear independence condition. Any questions? Do you see the overall line of thought on what we did here? Yeah, so we looked at the landscape of orthogonal tensors and we argued we can recover an orthogonal decomposition correctly, and then we're gonna transform our moments to such an orthogonal tensor, right? And that would have been invertible under like being linearly independent, which is essentially the subspace can then have the same rank orthogonal system to represent it. So that's kind of how we can use third order moments to recover mixtures of Gaussian in the spherical case. There is a whole class of models that can have the same form, so don't worry about this. The hidden Markov model is another class. So here the difference from Gaussian mixture is here you're having a temporal dependence, right? So there is a hidden variable that does a Markovian transition in each time point, and now you also have an observation, right? So given that hidden variable, you're observing some variable x. So these are hidden Markov models, so hopefully you've seen them before, right? And these are also hard to estimate because they have latent variables. So these models may seem very different. The hidden Markov model in the first glance looks nothing like Gaussian mixture, but the key is again the same thing, right? So we'll think about like what is the relationship between observed variables and hidden variables. And in this case, if you look at 3 consecutive measurements and ask, can I look at, how is this hidden variables related to the observed variables? So if you just look 3 of them, right, you can marginalize H1 and H3. Like those 2 hidden variables you cannot directly identify them, right? Because it's just in the middle, like that's not enough to uniquely identify what H1 and H2 are. So instead what you will get is, this system where this H2 is related to these 3 observed variables that are consecutive measurements, right? And this is also like, here there is conditional independence, right? So if I condition on H2, these 3 parts are conditionally independent. And we can use a lot of very similar ideas from the Gaussian mixture case to come up with the moments, right? So again, I can think of what is the moment between x1 and x2. So that's nothing but the cross correlation between 2 consecutive measurements of my observation, in a hidden Markov model. Similarly, I can think of 3 consecutive measurements, which is now the cross correlation between 3 consecutive measurements in my HMM model. And but the key is this conditional independence, right? If I have this conditional independence, I can clarify how my hidden variable is affecting these moments. So I can still think about writing out right, like these moments in terms of like tensor decomposition. So I can ask, what is the form of this moment? So first I can condition on my hidden variable and then marginalize over hidden variable. Right, so this is the form of the moments that, if you recall, expectations I can condition and then I can marginalize over the conditioning variable. Right, and this is a very special form because conditional independence means I can separate out these parts. Right, and here kind of I'm giving expressions what each part is. Right, I can kind of say how each observed variable relates to my hidden variable. So don't worry about the actual details of the expressions, but the key part is this conditional independence here, right? So I can clearly write out how my hidden variable affects the observed and how that kind of plays into my moment forms. And so we can convert all these to the same kind of tensor decompositions and recover the parameters. So I'll stop here. There are a lot more references to kind of think about different models, but I hope I gave you like the basic idea of like how you can look beyond second order moments and look beyond matrices to solve some of these model estimation problems. Thank you.